Okay.
So, besides starting,
Yeah. Okay, so good afternoon. So today I will tell you about this relatively new idea for an axion detection experiment, which was first, okay, here's the light. It was first proposed by Ariel Arza and Pierre Sikivi in 2019 in this paper, and further explored by Ariel and myself in a longer paper where we go through in more detail through the proposal. And here you can see my artistic representation of the axion echo, which will become clearer towards the talk. So you have a bunch of photons and an axion, and this axion will decay into two photons, and one is going to go in the same direction of the photons you initially had, and the other one is going to come back towards us. Okay, now change page. Okay, so this is the idea. So we have some antenna, for example, a radio telescope, and we have axion dark matter all around us. What we're going to do is we're going to send a powerful beam out to space, a radio or microwave beam, to stimulate the decay of axions into two photons and detect that the photons come back, the photons that come back. So the keyword here is stimulate. And this keyword is going to give you, it has two implications. First of all, that you enhance the decay rate, so it's not completely hopeless. And second of all, that some of the photons are actually coming back towards us. So this I will explain to you better. See, here I'm showing you already our result. Just to spike your curiosity, okay? Please hold your questions until the end. But this is our sensitivity projections is the blue region here. For two different models of the dark matter in our galaxy. One is the one that we are all familiar with, so an isothermal sphere, where the local momentum distribution of the dark matter is a Maxwell-Boltzmann. And this is a more exotic model, which looks completely different. And I will tell you a bit about it later. Okay, so but you see, this is a quite interesting projection. So I will tell you how we got to this plot, okay? So this is the outline. First of all, I introduce the axion simulated decay. Then I will go in detail through the properties of the echo wave. And I will tell you what the power at ground level looks like and also how it is distributed in space. And then I will come to the sensitivity. And then as a bonus, I will show you some slides not made by myself, but made by Chuan Guo, the Shanghai Astronomical Observatory, who is trying to set up the very first axion experiment. Okay. Okay, you all know very well that axions and photons interact through this Lagrangian, and among the various phenomenology, we have axion decay into two photons. Okay, so of course, okay. It turns out that the rate of the decay rate of the axion implies an axion lifetime which is much larger than much larger than the age of the universe, which is good because we want it to be dark matter, but it's also bad because it's very difficult to detect, at least for this sort of masses. I mean, it's impossible to detect for these masses. But what happens is instead of having axions decaying in vacuum, we have axion decaying into a background of photons. Okay, so in this case, you can have an enhancement of the decay rate, no, what's going on? Okay, which is given by, so let's say you have a background of photons with momentum k, so the decay rate is enhanced by a factor which is the phase space density of these photons of momentum k. And this is very easy to see if we think in terms of particles and Hamiltonian. So the axion photon Hamiltonian is going to look something like this. So there's going to be prefactors, okay, but the structure is going to be something like this. So we have axion annihilation operator here. Here I assume that this axion is at rest, okay? And then by conservation of momentum, we have two photon creation operators. By conservation of momentum, one will create a photon of momentum k, and the other one will create a photon of momentum minus k. Okay, and now imagine that I'm not in vacuum, but I am in a background of photons. So I have an initial state, I need a lot of axions. And then let's say I also have a lot of photons. So you can imagine when I apply this operator to this state to calculate my decay rate, I will get a factor of square root of fk plus 1. This is just creation operator, like in quantum mechanics. So at the end, I will have one less, where is the pointer? I will have one less axion, one more photon that is exactly identical to the ones of the background. And I will have one photon that is coming back in the opposite direction. And as I said, because of this factor of square root of f that you get when you apply the creation operator, you will have your decay rate enhanced by a factor of f. Okay, so how big can this enhancement be? Like here, I just put in some numbers. So we can, f is related to the phase space density of the photon is related to the energy density of the photon per bandwidth, like in a given bandwidth, and times the axion mass to the third, I hope, or over, like I can get my dimensions correct. But okay, if you consider a beam, simulating beam of 1 kilowatt and an axion mass of 10 to the minus 5 eV with this bandwidth, 1 megahertz, and let's imagine this is this power is distributed over an area with a circular area with 1 meter diameter, and the length is t. So actually t cancels here, and we get an enhancement factor of order 10 to the 20. So this is a huge enhancement. Okay. Okay, so this was to give you an intuitive idea. Now I'm gonna abandon the particle description, and for the rest of this talk, I'm just gonna talk about waves. So we'll have a beam, the wave of the beam, and the wave of the echo. Okay, so if we do we take our axion photon Lagrangian and we do we do Euler-Lagrange equation of motion, we get this equation for the photon, where I have dropped all axion gradients, assuming that we have a non-relativistic axions which make up the dark matter. Okay, so this is the dominant term. Okay, so what do we do with this? So unfortunately, this G times A, I keep losing my pointer. G times A is a small quantity, okay? So this makes it axion detection difficult, but it allows us to solve this equation perturbatively. Okay, so I'm gonna put on the right-hand side here the photon, the field of the beam, okay, which satisfies the wave equation without a source term. So I'm gonna put the beam here, and here I'm gonna solve for the echo wave here, okay? So this becomes just a forced oscillator, basically. Okay, so let me actually go through this calculation just once with the next to simplest possible case. So the simplest possible case would be an axion at rest, but here I want to put some axion momentum because this is relevant to the discussion that comes later. So let's imagine I just have an axion field like this, so just one momentum mode, and I also have a beam, which is also just a plane wave, okay? And with some polarization vector and some amplitude. Okay, then I take my derivatives, I plug it into the equation, and I'm left with this equation here. So let's try to solve it. Okay, so I plug in an ansatz for my echo field here, in which, okay, I match the polarization, so the vector structure. And then here I put also a plane wave as to match here the momentum of my forcing term. And so this echo is almost a plane wave with this momentum, but I also put a slowly varying function here. Okay, so by slowly varying means that the derivative of this curly A is much smaller than omega times A itself. Okay, in this approximation, I can solve the equation. And so what happens is I will have this combination will appear. Okay, so I have here m over omega, and here I put this, the energy of the echo here is going to be the one required to conserve the momentum. And I will have this combination, which you see, this can be 0 if m is greater than omega. And when this is 0, I will have a resonance. Okay, let me write down the full solution so we can compare the beam and the echo. Okay, so this is the beam. Let's say this is a linear polarization. The first thing I see is that the echo is polarization is at 90 degrees with respect to the one of the beam. Then I have my small prefactor, okay? Depends of course on the strength of the beam. And then I have the wave, and you see here, importantly here I have a minus sign and here I have a plus sign, meaning that this one is propagating forward and this one is propagating backwards, okay? And then I have this small epsilon factor, and this term, this is going to enforce the resonance, okay? So you see that when epsilon equals 0, this one will become T, and it will, and my echo field will grow. Okay. So now you understand that this is a picture that I showed you in the beginning. Okay. So we have actually this one we are not seeing this the field for this photon we are not seeing. We should go to second order perturbation to see this one. We are seeing the beam, which is the blue, the green lines, that we're seeing the echo here coming back with momentum minus k plus p. Okay. And okay, let's look better at this resonance. So I said epsilon was from, okay, the previous page was the omega minus m minus the omega of the momentum k minus p, which I can expand for small p, and I get this resonance condition here. Okay, this tells me that my resonance is centered about at a factor m/2, which you could have imagined like unsurprisingly. But I can also have a resonance, it's shifted a bit by the component of the axion momentum along the direction propagation of the initial photon. So I will have, this is the resonance, if I have just one momentum mode for the axion, this is my resonance frequency for the beam, and the echo will come back with this frequency here. So shifted by P. And also because now I know that this momentum k at resonance has a length of m/2, and this is the transverse axion momentum is mv transverse. So I know that it comes back with this angle. Okay, which is, of course, this is of order 10 to the minus 3, but it's going to be relevant if the decay is happening very far from us. Okay. Finally, what I do, I have to integrate over the whole axion mode and over the whole momentum modes. And let's look a second what is the bandwidth of the echo signal. So here, let's imagine, so the black line here is, I put some Gaussians here just because we like Gaussians. And so the black line is the intensity of the beam, okay, as a function of the frequency. And let's imagine that I am at resonance. So here it's a bit shifted from m/2 because let's imagine I have some average axion momentum in the direction of propagation of k. Okay, so the resonance is here. And so what is the echo bandwidth here? So if I have a beam mode with omega shifted by p/2 from the central frequency, you can see resonate with an axion momentum, with an axion mode of momentum p. So basically, and then as I move by larger shifts compared to the central frequency here, I will not have any axion momentum to resonate with anymore. So basically, in this case, the echo bandwidth is determined by the axion bandwidth. Okay, while in this other case, when I have so the beam bandwidth is much smaller than the axion bandwidth, then all my beam modes can resonate with some axion momentum. So then the bandwidth is going to be given by the beam bandwidth. And also notice that the shift in frequency between the beam and the echo. Okay. Yeah. Ooh. Sorry, I
Like if I was just thinking of the exact same.
yeah. The width of the. Okay. Yes. Well, here the relevant one is the momentum distribution, because this is the resonance condition here. So it's not p squared, but it's p in this case. Yeah. 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 Well, okay. This is I will tell you. But so ideally, if I will say ideally, if let's say we are in the rest frame of the axion, and I keep my beam on forever, then it grows forever. My beam on forever. Yeah. In practice, first of all, I have to turn off my beam at some point, and then the axion transverse velocity is gonna stop the growth at some point, at least in the intensity at a given location. Yeah. So this is what I will discuss now. So, so what did I do when I saw this equation before? If you remember, I had a plane wave, and then to solve my echo equation, I just integrated from 0 to t. So what does it mean? It's like I have nothing. I don't have a beam at t equals 0, and then I turn it on, and suddenly I have a beam everywhere. So this is not physical, right? So the physical situation is this. So this is the one-dimensional case, which is simpler than what I call the three-dimensional case, which we're going to see next. So by one-dimensional, I mean that there's no axion transverse velocity, and also the beam, let's imagine it's just a cylinder, okay? It doesn't have any divergence like this. So so this is the situation, let's say, at 3 different times, at time which I all call t, okay? So what happens here? So at time t, if I turn on the beam at t equals 0, at time t, the height of the beam is t, okay? And I am receiving photons from the lower half of the beam, because, so let's say the decay can happen here at t over 2, only starting from a time t over 2, because before there was no beam there. And then they will take another time t over 2 to reach me, okay? So at any given time, I'm receiving photons only from a decay happening in the lower half of the beam. And in this one-dimensional case, they all hit the surface of the emitter, okay? And you see here that they assume, here I'm always assuming there are axion everywhere. So here my interaction region grows linearly with time. So my power is gonna grow linearly with time until I turn off the beam. And now the cylinder starts traveling away from me. And the size of the interaction zone doesn't grow anymore, it stays constant. So at this point, the power will stop at the value it had when I turned off the beam. Okay. And here, of course, here I'm also receiving, I'm still receiving decays also coming from here where there's no beam anymore that happened before in this area. Okay. So this is the one-dimensional case. So I will have a power growing linearly with t until I turn the beam off. So this is the expression we find. So what do we have? Okay, we have some prefactor. Then we have g square rho, as you could expect, coupling square times the dark matter density. Then we have this delta, which is some combination of the beam bandwidth and the axion bandwidth in the direction parallel to the beam. Then we have the beam power. Then we have this intersection between S is here the surface of the receiver, and S0 is the surface of the emitter. because in this case, the echo is coming back to the emitter. So if my receiver is another place, I don't receive anything, okay? And here T less, this is the minimum between T and T off, which I think I wrote. Okay. Okay, so this is the one-dimensional case, but this is not what happens because the axion has a velocity in all directions, not only in the direction parallel to the beam. What's good? Although if you want, is this? It's the beam. Like here, and I'm not talking about. Yeah. Yeah, exactly. Hmm? Yeah, well, it's the analogous. Yeah. F gamma, you mean the phase space density of the photons that I showed in the beginning? Yeah, it's that one. This is providing the background. I mean, otherwise, if I just had the spontaneous decay, then this would not depend on what I do. It's just axion decaying as when they wish. This is just one different way to talk in terms of waves rather than in terms of particles. Okay, so here I put some numbers because I figure you may be interested in seeing what sort of power we can create. So with this is, I think, a coupling for like a QCD axion of mass 10 to the -5, more or less, and some dark matter density and a beam of 1 kilowatt working for 1 hour over a bandwidth of kilohertz, we can get this sort of power. Okay. Okay, now let's switch to the 3-dimensional case. Oh, I'm running late. No, I'm not running late because we started later. Okay. Okay, so comparing to what we had before, so this prefactor is the same, but now instead of having this intersection between surfaces and T less, I define this quantity which has dimension of T, but of time, but is like to a function. The position on at the ground level. Okay, so for the next few slides, I'm gonna describe to you how this stuff behaves. Okay, this T, this curly T, which plays the role of the T in the one-dimensional case, and this encapsulates all the 3D effects. So to make some progress, we need to assume something for our beam. We need to plug in something for this A0. And we choose something that we can work with, which is this Gaussian beam. This is actually the shape of the beam emitted by a laser. We use it, let's say, as an approximation from for example, the central lobe of a dish antenna, of the emission pattern of the dish antenna. So what does this look like? Okay, so we assume it propagates in the Z direction. So here this R is the cylindrical R, so it's the coordinate in the plane perpendicular to the direction of propagation. And you see decays, the intensity, the magnetic field of the beam decays exponentially in the radial direction with this characteristic length scale, which is also a function of Z. So this is over the radius of the emitter here at low Z, and then it grows linearly with Z as we go further away. So this beam goes like this. And then we also have this term that gives a curvature of the wave fronts, which are not planes, but they're curved. So this is what we use for our calculations of the next part. Okay. Okay. Sorry, this thing? Because Yeah. This doesn't extend everywhere. It decays exponentially at some radius. Yeah, if that was your question.
I mean, is it the function of
Of what? V0. B0. No. This is just a function of Z and of R and of the frequency of the and of omega. Yeah. I mean, here we are just considering 1 omega here, and then we integrate at the end. I don't know if for practical reasons, if you have many omegas, then how it is distributed in an actual, I don't know. I mean, in this formula, this does not depend on B. Okay. Yeah, it depends on omega, yeah. Okay, so, now let's first consider the case where I have no axion dispersion, but I have some axion transverse velocity. Okay, so this is the same picture that I showed you before, but now the echo comes back with this angle. Okay, so you can imagine that, so this is the angle, and this is T/2 is the maximum distance from which the photons are coming. So you can see, the projection on the at ground level of this angle coming from a distance T/2 is going to be T times Vp. Okay, and then which means that when T becomes larger than R over Vp, the photons are going to start exiting. They're going to hit the ground outside of the emission region. Okay, so as you can see here, as they start coming from further and further away, they go out of the emission region. And then, and here, that will have a hot spot, basically from here to here, where the echo intensity will be distributed in this hot spot here. And then when I turn off the beam, the hotspot is going to start traveling in the direction of the axion velocity. Okay, so we can see this in more detail. So let me distinguish two cases. The case in which I turn off my beam before the echo has time to spread outside of the receiver. So my T off is less than this characteristic time. And here I'm plotting, okay, so here I'm plotting this is this curly T in units of R over Vp that enters the three-dimensional expression for the power I showed you before. And this is the coordinate in the direction of the axion velocity. So here the T, this curly T keeps growing linearly with T. I turn off the beam before the echo has times to spread laterally, and then it just keeps, it starts traveling away. Okay, and this was this Gaussian is the shape of the beam. Of course, I inherited from the beam, and this is also Gaussian traveling away. Okay, now what happens is that if I turn off the beam later, so after the echo has started to spread out. So initially, as long as the echo is still within the receiver, I have linear growth of the intensity. Okay, and then you see it starts traveling. And then when I'm in this regime where the echo travels back outside of the receiver, but the beam is still on, so my interaction region, my interaction volume is growing, I have a sort of compensation between these two effects. And you see that the intensity saturates. So the maximum value of the intensity doesn't grow anymore, even though the total power still grows because this sort of sausage forms here. And then when I turn off the beam, this sausage starts traveling. Okay, and so this is, I'm showing you, this is we got from some approximation, but here we did also simulation. This is the simulation of exactly what I just told you. Okay, so here the beam is on. Here here the time becomes greater than this time for the lateral spread, so the sausage starts forming. And then here I turn off the beam and the sausage starts traveling away. Okay. And then in the case instead of when there's no net axion velocity, but there's a dispersion, it's completely analogous, only now there's no preferred direction, but the echo spreads in all directions around the emission spot. And we have again two regimes. I turn off the beam before the echo has time to spread laterally. So the intensity will, actually here you don't see it, but it will stay at constant for a while until we reach this time, which in this case is R over delta VP, before it was R over VP. And then that intensity, maximum intensity drops because the echo spreads. And in the opposite case, in which I let the echo spread laterally before turning off the beam, I also have, as before, a saturation of the maximum value of the intensity here, and then it drops when I turn off the beam. Okay. And here's the simulation. Okay, yeah. The color scale here, this is the curly T normalized by, so let's look at, so it's normalized by, let's say, the relevant time scale here. So R over delta V in this case times some factor, so that the maximum value of this quantity I'm plotting should be 1. Yeah. Okay. Okay, so to the last part, the sensitivity. So now we did all this study to understand what we have to plug into our formula for the sensitivity, right? So here I'm showing this this picture from the Condon book, Essential Radio Astronomy, which shows how transparent our atmosphere is as a function of wavelength. And so the sensitivity I'm going to show you is going to be, so this determines in which, for which masses, axion masses, can we have some hope of doing this experiment, okay? Unless we want to put it on the moon or things like that. So about from 1 millimeter to 10 meter wavelengths, this is the mass, corresponding mass range I will show you in the sensitivity plot. Okay. Okay, so let's summarize the collected power based on all this discussion that I told you about saturation effects. So this is the same formula I showed you before, but now we know this is a curly T, okay? So let's imagine we have emitter of radius R and a concentric receiver or a radius RC, okay? And we know how this curly T behaves, and we also integrate it over the surface of the receiver. Okay, so here, yes, I have a box here. So why this? So this is the same plot I showed you before. So this is the minimum between T off, and this is a characteristic. This is the time scale over which the echo exits the receiver. Okay, because yeah, this is the curly T I showed you before, basically integrated over the receiver. So why? Because you see, if I turn off the beam before, why the minimum between the two? If I turn off the beam before this time scale, see here the maximum height, the value of the curly T is determined by T off. While if I let the intensity saturate, then the maximum value, it doesn't matter what T off is for the maximum value, is just determined by this R over VP. So this is why the minimum between the two enters here. So if this is larger than T off, then the height is T off. If T off is larger than this, then the height is this. Okay, so here I have the minimum. And then we have to compare signal to the noise. So we use the radiometer equation here. And what is the measurement time? Okay, the measurement time is the opposite of what of curly T, basically, because we want to measure until the intensity drops. Okay, and in this case, the intensity drops in the receiver, which is this. So let's say the receiver is shaded in this shaded area. The intensity drop when the echo starts spreading, now starts traveling laterally, which in this case is R over VP, right? And in the opposite case, it starts traveling laterally at T off. So this is the, before I had the minimum in the power, and here I have the maximum. Okay, because I want to stop measuring when the intensity drops. And the bandwidth I showed you before, okay? So now we have all the ingredients, we plug it into the radiometer equation and we get our sensitivity estimate. So let me say a few words about these dark matter models. So I guess you are familiar with this, Maxwell-Boltzmann axion velocity distribution. I guess there is some uncertainties on the exact value of the parameter. So here we put an optimistic dark matter density and maybe, and these values for the average velocity and velocity dispersion. For making this plot, we assume that we can point the beam in the direction of the velocity of the sun towards the dark matter halo, so that this is 0 for this plot. This is limited only by the dV. And this is a more exotic model, for the details of which I refer you to Piasikivi's talk on Wednesday, as I think he's gonna talk about it. But in this model, the local dark matter density is dominated by just one cold flow of axions, which has a slightly larger energy density, and it is extremely cold. So this, the velocity dispersion is over the tens of meters per second instead of hundreds of kilometers per second. Okay, and it's thought that we know the direction of this cold flow, of the momentum of this cold flow, and we can reduce with some uncertainty, which corresponds to an uncertainty of the. So we think we know where to point the beam with some uncertainty, which corresponds that we cannot reduce the transverse velocity less than 5 kilometers per second. So this is what limits the growth of the signal here.
So this matter model also changes the surface of standard haloscopes.
Yes. Yeah, there are papers about these with Sikivi and Duffy, I'm sure. There are papers where they explore these things. Yeah. Mm-hmm. Yeah. Yeah, it's, well, it's the next slide. Okay, okay, so here. So we have two lines here. For each of these models, we have a solid line and a dashed line. So the solid line is this. So we assume signal to noise of 5. And we assume that we have an energy of 10 megawatt year to spend, okay? We also assume like this low noise temperature, 20 Kelvin, and this is the radius of the emitter, this is the radius of the receiver, we assume. If you plug this stuff into the signal to noise formula and you optimize delta omega and T off, which are the experimental parameters that we can choose, you get the solid line here. Okay. Actually, it turns out that when you do this, the signal to noise is maximized for T off as small as possible. But of course, if I make T off as small as possible, it means I have to give a huge power because my beam is on only for a short time. So this may be unphysical. So that's why we did also the dash line, in which case I have the same energy available, but I'm also say I want to have maximum 10 megawatts. I have a source of 10 megawatts working for 1 year. And now this is how we get the dash line, which is a bit worse. And okay, here we're going to need, for practical purposes, we're going to need to rely on our experimentalist friends to tell us what we can and cannot do in practice. Yeah. So in this case, It takes 1 year to cover a factor of 2 in axion mass. Yeah, this is, I didn't say it is for a factor of 2 in axion mass, yeah. In the other case, less, because the beam is on, if you're assuming that the beam is on at all time. If I had to choose where to start? No. No, we haven't started anything. I don't, no. It's just, there's a setup, but we haven't started doing anything, yeah. But I guess, I don't know, I don't know, actually, where do you start? Maybe, well, it depends on also what instrument available you have. I don't, yeah.
For the connection, you don't have any problem. There is no preferred region.
So this, well, it depends on the axion velocity, right? So for this one, we just assume that there's the receiver is concentric to the emitter, and in this case, basically, this is the case of the echo spreading in all directions, and this is the case of the echo spreading just in one direction. Then I guess you can, yeah, it depends on also, there's going to be, of course, depending on the orientation of the sun, the velocity of the sun, the velocity of the earth, etc. One should figure out where to put this hotspot is gonna move on the ground level. Yeah. Yeah, I think so. Yeah. You mean what fraction of the receiver area is? Yeah, 100%. Yeah.
So like if your cross goes all the way to like 10⁻⁶. It's those masses is the wave effect.
The wave effect?
Yeah.
You mean that I have only a finite number of wavelengths within my receiver?
Well, yeah, like a laser would be like something like meter wave with
yeah,
megawatt power.
Mm-hmm.
Is the wave effect important when you are sizes?
What do you mean by wave effect?
It's like zero diffraction.
A diffraction. Yeah, probably. We are not so sophisticated in this estimate, so we should, yeah, it maybe I don't know. We don't take this into account. Okay. In mass.
Yeah, next. First, you said there is a window.
Yeah, this corresponds to the window where the atmosphere is transparent. No, not on, unless you go to space or, yeah.
It's a kind of a lucky coincidence.
Right. Yeah.
The log scale.
Yeah. Okay. Well, so let's talk about the atmosphere, because yes, it is transparent, but it's not completely transparent. In fact, we have a ionosphere, which contains, charge atoms and molecules, and this may interact with the beam, and there will be a reflection from the ionosphere. So here, in this plot I'm showing, so the color here is the height of the beam at the saturation time, okay? So let's imagine that we let it saturate. This is the color represents the height of the beam. Here is a log 10 of the height in kilometers. And so here we have the radius of the receiver, which I set to be twice the radius of the emitter. And here we have the characteristic velocity scale. the characteristic velocity that determines that enters the saturation. So for the isothermal, the characteristic velocity is determined by the velocity dispersion. So we are here. So you see, of course, the bigger the receiver, the longer I can receive a signal for, but then I am gonna hit the ionosphere here, because this is the height. These black lines are the height of the 3 layers of the ionosphere. I think it's 60, 90, and 150 kilometers. And for the caustic ring, since the transverse velocity is only 5 kilometers per second, then my beam at the saturation is going to be much higher. So I'm definitely going to hit the ionosphere. So I will have some reflection from the ionosphere. Okay, is this the end of the world? Hopefully not. So remember that the frequency of the beam and the frequency of the echo are not the same, but they're shifted because of the axion momentum along the direction of the beam. So here, this represents in some unit my beam, and this represents the echo at several times. This is from the simulation of the isothermal sphere I showed you before. And so see, there is a separation with this distance here is the axion momentum along the direction of the beam. And this is of order hundreds of kilometers per second, which is much larger than the escape velocity from Earth. So we can hope that any reflection from the ionosphere is going to come more around here and can still be separated from the echo of the signal. Another thing is that this beam doesn't need to be pointed in the vertical direction, so it can be pointed like this. And then in this case, the reflection from the ionosphere is going to end up somewhere else, like reflect like a mirror, but the echo is coming back towards us. So this is also another thing that gives us hope, okay? And this, I think, one just has to try and see what comes back, okay, and see how bad we are going to mess up with the ionosphere with this powerful beam. Okay, so this is the end of my slides. So now I will show you the slides that have been given to me by Xuan Guo, whom I talked with last week, and he's trying to repurpose some of the equipment they have to set up the first prototype echo experiment. Okay, so they have identified a site which is in a remote region in China, which is called Dunhuang, if I remember correctly. And it's basically in the desert. And here I show you their measure of the radio frequency interference, which is good. There are only two peaks of radio frequency interference, but it's a quite quiet area. So this would be good. And they already have an antenna there, which is this. They have this antenna, which could be the receiver. Right now, they told me it can receive in this frequency, but he told me that there's a filter that they can remove to bring this up to 1 gigahertz. And this is instead the antenna that they're envisioning for emitting the beam, which they already have. It's cheap and it's easy to get. And okay, here I show you this some equipment they have. I don't really know how to describe it to you very well, but they have in place the data acquisition system and the data saving system. This is ready, okay, to use in this remote. Yes. No problem. Yeah, I mean, you have to attach it to something, but this is just it has to be attached to a transmission unit. But so what he told me is that they plan to use this one to emit the beam and this one to receive the. Okay, this is the part that is not yet ready. So the emission unit, they don't have. But they're thinking to use one of these units that they use for radars. So radars also emit, radio waves or microwaves, and they look for the reflection. And these things can emit power of kilowatts for sure. And there are some new technologies can get to the megawatt. Of course, we're not going to start with a megawatt source I don't even know if this antenna can survive it, but yeah, so once they have the emission unit and they're thinking to recycle something from the radar experiments, then we can start with the first prototype. This is, yeah, power. Sorry, which one? No, but this is, I don't know what this means. This is not the transmitter. This is just their data acquisition system. Yeah. It has nothing to do with the meter. Okay, so stay tuned, and that's it.
It's about Elisa and the questions. So
why are you stopping? What about what happens if the ionosphere bounces back down?
Okay. Okay, sure, good point. Yeah. Yeah, this is something that we have to test, I think. Like, I mean, I don't know, but from my point of view, the first thing this prototype experiment should do is to see what comes back from the ionosphere and see how bad it is. Of course, this is a function of the power of the beam that you send. Like for low powers, there shouldn't be much problem. Then if you get to 1 megawatt, eventually, I don't know. Yeah, but yeah, good point. Thanks. I think so. Yeah, you have to. So here, I assume. So this spreads laterally. This represents just the velocity of the sun, but of course, that's the velocity of the Earth orbital and the rotational. So yeah, this is also gonna change. Yeah. So. I mean, I think so. Let me think. So we said in the thing goes for 1 year, but in pulses, the pulses are depending on the dark matter model can be 1 second or 1 millisecond the duration of a pulse. Then if you have many, yeah, it will come. Yeah, one has to think the best way to put your receiver. Yeah, it's more complicated than this, of course. Yeah. I don't know, because the main component is the velocity of the sun. So this is only one direction, right? Yeah, this dominates.
Is that interesting? Or do you really just run? I mean, it takes for all this same thing, and I really just run this like thinking that it's I just follow this as like a simple harmonic oscillator.
Yeah. Because of the you mean the time growth, it will get yeah. I don't think so. I mean, I don't see it from this calculation seems. Yeah. Okay, well, it seems just that you have a different frequency for the beam. You have another plane wave. This will resonate with another Axion mode. And I don't know if I'm answering your question. I don't know. So it doesn't seem like.
It seems that the growth that you were getting was because you had sign of epsilon B, over epsilon.
Yes,
And then if epsilon is small, then that goes like T.
yeah.
But I guess epsilon is small, arbitrarily zero, right? So at long enough T, right, as compared to the epsilon that is in zero, I guess that you don't have that anymore, right?
Maybe. I mean, here what I don't know, maybe if this can answer partially your question, Nick. Okay, let me. So here I didn't show, but so basically what happens here, when you calculate this stuff, you have to square this, right? And then you have this squared, this becomes, one of these becomes a T and the other one becomes a delta function. And this is gonna select one momentum mode of the beam or of the axion momentum. So I don't know if this answers your question. Yeah, okay. Yeah. Well, one of the first comments I got when I talked about this is that we are gonna destroy some satellite or something like that. So we have to be careful, I guess, not to hit stuff that's orbiting Earth. Yeah. Yeah. Hmm? Animals, yeah, yeah, sure. Yeah, I don't know what animals they have in this desert in China. Hopefully, not many. Yeah. Mm-hmm. Okay. Yeah. Solar system radar, okay. Ah, okay. So you mean one could take the data and repurpose it?
Yeah.
Okay. Okay. Okay, thank you. Maybe later I ask you to give me the name. Okay, thanks.
The questions? This have to be materials time.
Maybe. Yeah, I don't know. Probably you need a clear sky. Yeah, I don't know if how this transmission coefficient changes with the weather. Yeah, I don't know. Mm.
Yes.
So the returning echo is orthogonal to the initial polarization.
Yeah. Yeah, absolutely. Yeah. Yes. Yeah. Yes.
Of course, you can continue discussing offline. It's very on the work. All right,
Okay.
so let's thank Elisa again.
Thank you.